What's up, mathematicians? Today we're going to review section 1.6. It's all about inverse functions and logarithms. So first, let's start off by defining a new type of function. So a function f of x is 1 to 1. So we write 1 to 1 on a domain if f at x1 does not equal f at x2 when x1 does not equal x2 in the domain. Right, so I can't have two outputs equal each other if my inputs don't equal each other. So I put in one input, I get one output, that's a function. For every output, there's only one input that gets me to that output. So some functions are 1 to 1 on a smaller domain. So what I mean by that is instead of its whole domain, I can exclude part of its domain and then it'll be 1 to 1. So let's look at x squared. Well, that obviously isn't a 1-to-1 function, right? So if f of x equals x squared, well, I know that f at -1 is 1 and f at 1 is also 1. So it's not a 1-to-1 function. I have two inputs that give me the same output. Well, what if I just restrict this to when x is greater than or equal to 0? Then I just get one side of the function, and that now is 1-to-1. So that's what we mean by saying that some functions are 1-to-1 on a smaller domain. So another way that we can test 1-to-1-ness, if you want to call it that, we have the vertical line test to test if it's a function. So now we have the horizontal line test. So a function, let's call it y equals f of x, is 1-to-1. That's how I write it sometimes. If and only if its graph intersects each horizontal line at most once. So looking back at if I restricted x squared to only positive values of x, that passes the horizontal line test. If we go back and look at this guy, the whole domain, we see that it doesn't pass the horizontal line test. So that's a fun graphical tool for you guys to use if seeing if something is 1-to-1. So then we'll talk about the definition of an inverse function. So suppose we have a function f. And suppose that f is 1 to 1 on the domain D with range R. The inverse function f to the negative 1 is defined as f to the negative 1 of b equals a if f of a equals b. We say this f to the negative 1 as f inverse. So the domain of f inverse is R, and the range is D. So we flipped everything, basically. So cool. How do I find the inverse, though, right? I know all these properties, but how can I find it? Well, if I'm just given a graph, we can talk about it graphically. If I'm given that was a terrible graph. There we go. We can draw something like this. And then its inverse is going to, let's see if I can do this right. Something like that. You can see that it's mirrored. If I was a better drawer, it'd be a little more clear about this line. So the graph of the inverse of f is the reflection of f about, or let's say across y equals x, all right? So what if we're just given an equation and we're asked to find? So there's two different ways. They're basically the same way, but two different steps. Our first step is we can interchange x and y and then solve for y. Or we solve for x and then interchange x and y. Interchange kind of means like we're going to switch them. So I'm going to say solve for x. Make that look a little nicer. Okay. So let's do a quick example of that. So say we're given y equal to 1/2 x plus 1. Well, step 1 says to interchange x and y. So now I'm going to have x equal to 1/2 y plus 1. Okay. Well, step 2 says solve for y. So I'm going to subtract 1 from both sides. So I get x minus 1 equals 1/2 y, and then multiply each side by 2. So I have 2 x minus 1 equal to y, or y equals 2x minus 2. And that's our inverse. So not all functions have inverses, but most of them do. So we just talked about the exponential function. It has a very special inverse called the logarithmic. No, I always spell this wrong. Logarithmic. Functions. You can also just call them log functions because that's what I call them. So the log functions with base a, they look like y equals log base a of x is the inverse of the exponential function y equals a to the x. Remember here, a is greater than 0. So we have two specific types of log functions. There's one that we like to call the natural log, right? We have the natural exponential, so now we have the natural log. That is log base, can you guess it? It's e. We write that as ln of x for the natural log. And then we also have something called the common log. And if you ever just see a log without a base on it, it's because it's log base 10. I think if you have like a scientific calculator, it says log x and ln of x. Log x is log base 10. So I want you guys to take note of some fun things about log and ln of x. So they're inverses, so ln of x equals y whenever e to the y equals x. Also, ln of just e, not e to the x, e equals 1. And ln of 1 is 0. Okay? So just like we had some exponential rules, we had log rules. These seem a little less intuitive than exponential ones, but I think they're really cool. So we're going to let a be greater than 0 and b be greater than 0. And they're just going to be numbers. Right? So the first log rule is product rule. If I have ln of a times b, I can rewrite that as ln of a plus ln of b. It's called product rule because a and b are being multiplied inside of ln. So the next one is quotient. So ln of a divided by b is going to be ln of a minus ln of b. Third rule is the reciprocal rule. So ln of 1 divided by x. Oh, not x. Let's keep it a. I can rewrite that as just negative ln of a. And number 4 is power rule, which is my favorite log rule and also maybe the most useful one. So if I have ln of a raised to the b, I can write that as b times ln of a. So this is when b is raised to the a, not ln of a raised to the b. It's very different. So what are some cases where I can use these rules? So we can use it for when ln of x plus 1, 2x minus 3. How can I simplify that? Well, quotient rule says I can subtract the ln of the numerator, x plus 1, minus ln of 2x minus 3, the denominator. Even though these are added inside of the ln, I can't split them up anymore. There's a 2 in front of this x. Oh, they're multiplied together. I can't do that because there's an addition right here. This subtraction and addition kind of stops you from moving on anymore. And then if we have ln of 1 divided by 8, well, the reciprocal rule says that that's just the negative ln of 8. Well, I know that 8 is just 2 cubed. So now I can use the power rule, and the 3 comes outside. Negative times 3 is just a negative 3, ln of 2. So inverse functions have a fun property. So if the composite of inverse functions. That means if I do f of f inverse of x, that's going to equal f inverse of f of x, and that's going to equal x. This is a very important rule that we're going to use to show some other cool things about logs. So okay, cool. I was making sure that I was doing that at the right time. So what about, those were like natural log rules, right? We talked about log with base e, but what about the inverse of a to the x and log base a? So we kind of talked about earlier that these two are the inverse of each other. So if I plug in, so if we just keep it a, if I put log base a of x into a to the x, I'm going to get a to the log base a of x. Well, putting composing inverses of functions, I'm just going to get x back out. And if I do log base a of a to the x, same thing's going to happen. I'm going to get x back out. Same thing works for base e. We can get e to the ln of, not e, what am I doing? X, which is going to equal x, and ln of e to the x will also equal x. So this also allows us to kind of rewrite a to the x as a function with e to the x in it. So what I mean by that is a to the x is going to equal e to the ln of a to the x. We're using this right up here. Well, then a is raised to the x power, so using log rules, the power rule, x is going to come out front. I'm going to have ln of a. And I can rewrite that nicely. Since ln of a is just a number, x is my variable. So I usually like to write it ln of a as the coefficient of x. This also yields what is called the change of base formula. Right, so I can rewrite ln of x as, well, I know that if I put log base a of a to x, that's just going to equal x. So ln of, oh, also a to the log base a of x equal x. That's what we're going to use. So ln of a to the log base a of x. Those two things are equal. Now using log rules, power rule, so this log base a of x is an exponent, so it's going to come down. So we'll be left with ln of a. And then I can divide by ln of a on both sides. And I get that log base a of x is the same as ln of x divided by the ln of a. Let me rewrite that because that was a little messy. This is what we call the change of base formula. So when can we use these things? Well, do you remember that problem from last section 1.5? We wanted to double our investment and know how long that took. So we wanted to double our investment and we had a rate of 6.25%. So we got that we needed 2p equal to p 1.0625x. We divided by p on both sides, so we got that 2 equals 1.0625x. And I just didn't know how to, the x is up in the exponent. We could have just like double checked and everything. It just would have been just clicking numbers in the calculator, which isn't real math. Well, I can now take the ln of both sides. So I can ln both sides. So we're going to have ln of 2 equal to the ln of 1.0625x. Power rule says that x is going to become a coefficient. So I have x times the ln of 1.0625, and I can divide and that's what x is going to equal. Once you plug that into your calculator, you get that x is about approximately 11.433 years. Awesome. We can also use this for exponential decay. So let's scroll up a little bit. There we go. So if we consider the half-life of some radioactive element, what that means is the half-life is the time, the amount of time it takes for half of the sample to decay away. So time, oh no, the amount of time. So if in 100 years there's half of it left, its half-life is 100 years. So the amount of time So if you remember our exponential decay function, it is y equals y naught e to the negative kt. We just made k negative here. So k is a positive number, so negative k is a negative number. If we're doing half-life, well, that's when y equals y naught divided by 2, half of it, right? So we're going to get 1/2 y naught equal to y naught e to the negative kt. Well, these two are going to cancel out. I'll get 1/2 equal to e to the negative kt. Well, I know I can get rid of that e by taking the ln of both sides. So I get ln of 1/2 equal to negative kt. So half-life divide by negative k. Ooh, yeah. Before I divide by negative k, I'm going to rewrite ln of 1/2 using the reciprocal rule. So I'm going to use negative ln of 2 equal to negative kt, and then divide by k. So that will get ln of 2 divided by k equals t. Then my negatives will cancel out. Reciprocal. All right, cool. So if we simplify that a little bit, we just get that t equals the ln of 2 divided by k. Depending on k, that'll change the half-life. So that is all about inverse of exponential functions. We also have a group of family of functions that are the inverse trig functions. Well, Mackenzie, trig functions, I know the graph of sine, it's not 1-to-1, but we can restrict that onto a smaller domain. So for sine, we can restrict it to being between negative pi over 2 and pi over 2, and I can restrict cosine to be from 0 to pi. That way, that little subsection of the domain passes the 1-to-1 test, and it also has all of the numbers in the total range. So we're not kicking anyone out of the range, I'm just shortening my domain. So each of the 6 trig functions has its inverse. So we can do, let's say, the original, and then its inverse. All right, so sine of x, its inverse is arcsine of x, or we can also write that as sine inverse of x. Cosine of x, arc cosine of x. I bet you can guess the other 3. So I want you guys to make an important note that sine inverse of x is not the multiplicative inverse. So I'm not saying 1 over sine of x. Because that equals what? What's 1 over sine? It's cosecant. Those things aren't equal. Arcsine is a completely different type of function. So remember that kind of what I said earlier, that y equal to sine of negative 1x, sine inverse of x, is going to be a number in the range pi over 2, negative pi over 2 and pi over 2. If y equals cosine inverse of x, it's going to be a number in between 0 and pi. Ooh, that's a hard bracket. There we go. So let's do a few examples to kind of reiterate what I mean. So if I ask you to evaluate, there we go, arcsine of 1/2. Well, this implies, so if arcsine of 1/2 equals some x, then sine of x equals 1/2. Well, I know that every iteration of pi over 6, or most of them, are going to give me a positive 1/2, right? So pi over 6, 5 pi over 6, and so on. But, so pi over 6, 5 pi over 6, what else? What's another one? If I add 2 to that, What about negative? No, not negative. And so on, right? So, but I'm only between negative pi over 2 and pi over 2. So I need to choose one. Well, the only one in this iteration is pi over 6. So I can say that arc sine of 1/2 is pi over 6. What about if I ask for arc sine of negative 1/2? Well, that means that sine of x equals negative 1/2. That's true at negative pi over 6, 7 pi over 6, 11. Oh no, my pen broke. Anyways, but as you can see, the only one in that I need negative pi over 6 to be in between negative 1/2 and 1/2. So that's why we need to choose negative pi over 6. All right? So that's all that I had time today for. You guys have homework due on this now. Let me know if you have any questions.